For our second example in section 7.2, I want to do a defective example for you. So classify the matrix as defective or non-defective. Spoiler alert, Dumbledore dies. I mean, the matrix is defective. Let's get into this. Now, another thing that I want to show you in this video is the subtle art that is finding the characteristic polynomial and factoring. So please pay attention to how I do this. Okay, here we go. Let's dive right in. Classify the matrix as defective or non-defective. We need to determine if it has a complete set of eigenvectors. So let's get started. Again, we'll start with the characteristic polynomial. That's going to be the determinant of a minus lambda I, which here is going to be the determinant of a 3 by 3, which is negative 1 minus lambda 2, 2, negative 4, 5 minus lambda 2, and negative 4, 2, 5 minus lambda. Now, expanding right across the top row here, old school, I'm going to get the following. Let's go over here and make some more room. This is going to be negative 1 minus lambda times the 2 by 2, 5 minus lambda 2, 2, 5 minus lambda, minus 2 times the 2 by 2, negative 4, 2, negative 4, 5 minus lambda, plus 2 times the 2 by 2, negative 4, 5 minus lambda, negative 4, 2. Cleaning this up just a little bit, this is going to be negative 1 minus lambda times, 5 minus lambda squared minus 4. Minus 2 times the 2. I'm doing Twinkie products here, by the way. Twinkies. This is going to be negative 4 times 5 minus lambda plus 8. And then 2 times negative 8 plus 4 times 5 minus lambda, as I adjust some of those negative signs while I subtract my Twinkie products there. So watch out for those double and triple negatives. So this is negative lambda plus 1 as I factor out a negative 1 there. And this is going to be lambda squared minus 10 lambda plus 25 minus 24 is plus 21 minus 2 times 4 lambda minus 12. Looks like I'm missing a plus sign up there. Plus 2 times negative 4 lambda plus 12. And I'm not going to create a cubic. Do not create a cubic. That's maybe the subtle part there. So let's just keep factoring as best we can. This is lambda minus 3 times lambda minus 7. This is negative 8 times lambda minus 3. And this is also negative 8 times lambda minus 3, or negative lambda plus 1 times lambda minus 3 times lambda minus 7 minus 16 times lambda minus 3. And the subtle part here is both of these have a factor of lambda minus 3. And now we're going to factor some more. This is lambda minus 3 times the quantity negative lambda plus 1 times lambda minus 7 minus 16, which will simplify to be lambda minus 3. If I factor out a negative sign out of that second polynomial, this will become a lambda squared minus 6 lambda minus 7 plus 16, which will be a plus 9, and this will factor as negative lambda minus 3 times lambda minus 3 times lambda minus 3, or negative lambda minus 3 cubed. And so our eigenvalues here, we only have one of them. It's lambda 1 is equal to 3 with an algebraic multiplicity of 3. So we're supposed to classify this matrix as being defective or non-defective. I told you it was going to be a defective example. What can we expect here? Well, if it's going to be non-defective, it's going to have to actually generate 3 linearly independent eigenvectors here. That is to say, my eigenspace is going to have dimension 3. Anything less and it's going to be a defective matrix, which is what I expect to happen here, given the name of this example. So we're just going to dive right in here. Our only case lambda 1 is equal to 3. We get A minus lambda 1I is equal to the matrix, let's see here, subtracting 3 down the diagonal here, we're going to get, let me just grab this for reference so I don't make a mistake. -1 minus 3 more is -4, 2, 2, -4, 5 minus 3 is 2, 2, and -4, 2, 2. And so the row reduction there shouldn't give us too much trouble. This is row equivalent to 2, -1, -1, 0, 0, 0, 0, 0, 0. Now, I'm not going to actually REF that because I don't want to deal with fractions, but it's pretty straightforward. I can actually see that I'm only going to get 2 eigenvectors here because I have 2 free variables, or I have 2 missing pivots. But let's go through the motions. This row 3 says that x3 of my vector is going to be free. Row 2 says x2 of my vector is also going to be free. And row 1 says 2x1s are equal to s plus t. So the vector v that we're looking for here is 1/2 s plus 1/2 t, s and t, which if we decompose this and we factor out s, we're going to have 1/2, 1, 0 plus t times 1/2, 0, 1. And if we're clever about this, we could say let s equal 2 and t equal 0 so that we don't have any fractions. And then my first eigenvector will be 1, 2, 0. And if we let s equal 0 but t equal 2, our second eigenvector will be 1, 0, 2. And so this is going to mean that our only eigenspace is the span of the vectors 1, 2, 0 and 1, 0, 2. This is our eigenspace, and my tablet is freezing. Hold on a second. It doesn't want to recognize my hand gestures here at all. Pardon the interruption. So this is a basis for our eigenspace. So the set 1, 2, 0, 1, 0, 2 is a basis for our eigenspace, which has dimension 2. So in this particular case, we're not actually able to form an eigenbasis for all of R3. Or, since the algebraic multiplicity of lambda 1 is 3, which is not equal to the dimension of the eigenspace, which is our geometric multiplicity, equal to 2, A is defective. The end.